Hey everybody, hope you're having a great day. It's Mr. Ray. We're going to continue on with our data management course. Today we're starting Unit 2. Unit 1 was looking at different ways of counting more complex situations. So you learned quite a few tools to accomplish that. Unit 2 is kind of extending that now that we know how to count things in a variety of ways. Now we're going to actually calculate the probability of something happening. So probability is a branch of mathematics, and we will be spending most of the rest of the course talking about probability. So Unit 2 is the introduction to probability, and we'll be doing 2 other units that are looking at very important methods of probability, the normal distribution and other types of distribution. So it's a very important concept, and we're going to today talk about some of the basics of probability. So when we measure probability of something, we can either measure it as a fraction or a decimal or a percentage. So if you think about percentage, if you talk about probability, it can be anywhere from 0 to 100%. Probability of 0% means it's never going to happen, and 100% probability means it definitely will happen. So, and you can convert the percentage into a decimal. For example, 100% would be 1, and 0% would be 0. So, as a decimal, the value will be between 0 and 1, and you're going to include some decimal points there as well. So, for example, a probability of 0.75 is the same as saying there's a 75% likelihood of that happening. When we do a lot of our calculations, we will get a fraction, like 9/16 or something like that. So you can convert that into a decimal as long as you don't round improperly or too early. Give a couple of decimals of precision if there are decimals after. Well, just do your rounding correctly. Depending on the question, I'm pretty much accepting of any one of the 3 ways of formatting your answer: fraction, decimal, or percentage. I think in most courses it's usually done as a decimal, but if I'm looking for a particular format, for example, the question might say, what's the percentage of something happening? Then obviously you give it in percent. So now, a lot of these things I'm going to talk about in a second, but I want to start with there's 3 ways of actually determining probability of something happening. So the first way is experimental, which is also another word for that is empirical. So you actually conduct an experiment, and I'm going to give an example of how that works in just a few seconds. So there's experimental, where you calculate the probability through experiment. There's also theoretical, where you just look at the mathematical probabilities. So basically we're going to use the numbers that we calculated in the first unit and do as a fraction. So we'll get more into that as well. And the last one is subjective, which is just kind of a guesswork. So we will be looking at more in the theoretical and experimental probabilities, but this is a third option here where it's like a gut feeling. I feel like I feel like I've got a 75% chance of passing this test. So that's not based on any kind of in-depth analysis or mathematics. It's just my gut feeling. So that's the third way. So I just want to give a quick little sample of what some of these terminologies mean. I know it can be a little bit overwhelming getting all these new words at the same time. So I'm going to start with a situation. You have you have a single die, and just so you know, the singular of dice is die. So there's one die or two dice or three dice. So I will try to obey that law. If I refer to one, it's a die. If it's more than one, it's dice. Forgive me if I don't follow that exactly. But when you see it in the book and you see the word die, it just means a single version of dice, one die. Okay, so if I was to look at rolling a die, so just one, and obviously hopefully everybody knows there's 6 sides to the die, and we will assume there's an equal chance of it landing on any one of those numbers, which most die are fair like that, not all of them. Now, the first thing I'm going to look at is the outcomes. Okay, so if I roll a die, the outcomes refers to all the possible results that I could get from that action. So with rolling a die, I could get a 1, a 2, 3, 4, 5, or 6. Okay, now those are the outcomes. How many do we have? We have 6, obviously. So the number of outcomes is equal to 6. And this is a terminology that you'll see quite often, we used a little bit of it in the first unit, but it will continue. So this is almost like a function with a little n here. So basically it means the number of outcomes. So here's a list of the outcomes, the number of outcomes, you just add out the possible. So it's 6. It's not the highest one, it's just the count, 1, 2, 3, 4, 5. 6. There's 6 of these. Okay, so the number of outcomes is 6. So in this case, we also refer to this as NS. Okay, and this is the same terminology we use with Venn diagrams. So this would be the total number of, people in a situation, or the number of outcomes. So S is also used as the superset of all the possible outcomes. So the number of outcomes is 6. Now, once I've got that, I might want to say, I want to figure out what's the probability that I roll a 2. So we also have some new kind of not terminology, but mathematical notation. Whenever I want to get the probability of something, it's a capital P, and then inside I put probability of what. So you can start off by just saying what you're trying to find the probability of. Probability of rolling a 2. So it's like function notation. Probability of getting a 2. Now the way we get that, we're looking at the theoretical or the mathematical way of calculating probability. So what we do is we calculate on the top the number of ways of rolling a 2. And then on the bottom, we put the total number of outcomes, which we've just talked about. So in this situation, you've got number of ways of rolling a 2. Well, how many 2s are in the possible outcomes? Well, there's just the 1. So it's 1 over 6, because that's the total number of possible outcomes. So the probability is 1/6, and we can change this into a decimal. And now in this case, 1/6 is not a nice fraction. If you do 1 divided by 6 on your calculator, you get 0.166666, so on. So if we just round it to 2 decimals, we get 0.17. Well, and if we want to get percent, we just move the decimal place 2 to the right. So that's 17%. So the probability of rolling a 2 is 17%, or 0.17, or 1/6. Okay. Now this whole method we use here, this was the theoretical probability. Okay, this is all through mathematics and through fractions and possible outcomes and number of ways of getting what we're trying to get. So that's the theoretical, and I would say most of the most of the probabilities we do, we'll be using theoretical, but there's also where you can do experimental. So experimental is when you basically conduct an experiment. Conduct experiment, and the experiment is rolling a die. And you set this up yourself a certain number of times, rolling a die a certain number of times. We're going to track what we get each time. So in my experiment, we're going to roll the die 10 times. Okay, now that's probably on the low side if you want really good data, but so in this case, I roll the die 10 times, and what I do is another word for that. Each time I do this, these are called 10. This would be 10 trials. So every time you conduct one event of the experiment, and you're doing this over and over, that's called a trial. Okay, so in this case, 10 trials means that if I counted up the trials, I would get 10, obviously. So here's the notation here. Number of trials is equal to 10, and a short form for that would be n with a lowercase t, a number of trials. And you can see that compares with the, when we did theoretical, the number of outcomes. Okay, so instead of possible outcomes, which we did in theoretical, we actually conduct the experiment, and the trial is we're basically rolling a die. So in this case, we're counting how many trials we did, how many rolls. Okay, now say I did these 10 trials, and this is what I got. So I got a 5, a 4, a 6, 4, 3, a 3, 2, 1, 6, 5. Okay. So now this time you can see this should add up to 10. These are my 10 experiments or my 10 trials. So now when I do my probability of rolling a 2, okay, so this is now experimental probability. It's going to be, it might be the same number as this, but it might not be, because this is kind of random chance. So if I do probability of rolling a 2 now, I get, I count the number of times, number of trials where I got a 2, and that would be over the total number of trials. Okay, you can see it's a little bit similar to what we did here. So this is the number of outcomes of rolling a 2, which in this case was 1. This would be how many times we actually got a 2 when we did our experiment. So it could be 0, it could be 10. Okay, but in our case it was 1. So we got that 1 time, and the total number of trials we did was 10. So in this case, the probability of rolling a 2 with this experiment we conducted was 1 over 10, or 0.1, or 10%. Okay, now you can see the results we got, 10% versus 17%. They're not the same. Now what you'll probably see, as long as this die is a fair die, it's equally weighted, and there's an equal chance of getting each of these 6 numbers. Over time, as you conduct more and more trials, if I redid this with 100 trials, I might get something like 16%. And if I did it 1,000 times, I'm going to get closer and closer to the actual theoretical probability. Okay, obviously the lower the number here, like if I only rolled it once and I didn't get a 2, well, I would have got a 0%, but that's not a good experiment because it wasn't an adequate number of trials. Okay, so this is known as experimental probability. So these are the 2 types we'll be dealing with in this course. I would say the majority of what we do later on will be theoretical, but there will always be instances where I actually conduct an experiment. Okay, now the third type of probability was the subjective probability. So somebody might ask me, what's your gut feeling about your next roll? What what do you think the probability of your next roll being a 2 is? And I might say, well, I've got, I just got 2. I just rolled a 2 3 times in a row, so I'm feeling pretty good about this. So I think there's maybe a 50% chance that I get a 2. That's kind of faulty logic, but it's subjective because that's what I'm feeling. So the subjective probability is that gut feeling. It's not based on science. Well, it might have a little bit of underlying science, but it's certainly not something you can kind of back up through data and mathematics. Okay, so those are the 3 types of probability. So if I go back to the lesson here, hopefully these terms make more sense now. So the probability experiment, this is when you're conducting trials. Okay, a well-defined process consisting of a number of trials in which clearly distinguishable outcomes or possible results are observed. So this is us rolling the die, and the outcomes would be, rolling a 1, a 2, up to a 6. Okay, sample space. This is all the possible outcomes of whatever we're doing. And the events, we'll get to this a bit later, but what this really is, if I go back to when I talk about probability of doing something, sometimes when we calculate probability, what we're calculating the probability of is kind of a mouthful, like a big sentence. The probability of, of drawing a card between 2 and 7 and rolling an even number on your die, right? That might be something you're trying to calculate the probability of. Well, that's a real mouthful. You don't want to have to write that over and over and over. So what we do is, instead of rolling a 2 as what we're getting the probability of, we could actually define an event. Now the event would be, we just give it as a capital letter. We might say the event A is equal to rolling a 2. So later on, when we get down to this part, instead of saying probability of rolling a 2, we would say probability of A, capital A, which is defined earlier on as rolling a 2. Okay, so we'll see that in some of the examples. Okay, so that's what events are, and we usually, like it says here, we define the events as a capital letter. It's kind of like a variable, but it's a bit more than just a variable. It's not really an undefined thing. It's really just a label for something we're trying to calculate the probability of. Okay, and here we saw this in my example that I just did. Probability of any event happening is the likelihood of an event A will occur is P of A. Probability of A happening is the number of times it happened over the total number of possible outcomes. Okay, so it's always mathematically defined as a fraction. Even experimentally, it's a fraction. The difference being what we have on the top could be theoretical or an actual experiment number. Okay, I think I'm gonna just jump into some examples here, and then maybe go back, and you should see that those key concepts were taken care of and you understand them. So the first example is using something called a spinner, and this is something that's quite common in probabilities. It's just a cardboard circle divided up into some pie-shaped colored sections, and they might be labeled. Maybe it's to win prize money, who knows. So you've got this little arrow in the middle, which is centered in the middle of the circle, and you just flick it and it spins around, and it supposedly will point to a random section somewhere on that spinner. Okay, now this picture of the spinner, this is not the spinner we're using. Okay, I just wanted to put a picture of a spinner so you could, if you had no idea what a spinner is, you can get an idea from the picture. So our spinner definitely does not look like this in terms of the sections. And so what we've got here, so a student spins this mystery spinner. So I guess they spin it and they just record the color that you get from the section that it's pointing towards. So at the end, after 23 times, actually it's 24 times. Okay. We got red 12 times, yellow 4 times, and blue 8 times. Okay, now it says determine the experimental probability of the spin landing on each color. Express your answer as a fraction, a decimal, and a percent. So the first thing we do is add up the number. These are basically the trials we did. We did the results add up to 24, like we should match the number of times we spun it. So that's actually the total trials. They didn't, I guess they kind of told us that directly, but we have to make sure that that adds up to 24. Otherwise, some of the trials weren't recorded. And I can write that down as n of t, which means number of trials, is equal to 24. Okay, so I'm going to divide this into 3 sections, one for each color. So the probability, the first color, the probability of landing on red. Now you could put probability of red, but it's a lot more descriptive to say what you're actually finding the probability of it. Okay, landing on red is more descriptive than just red. Okay, now this is equal to the number of times that our trials landed on red over the total number of trials. So in our case, the number of times we landed on red was 12, and that's over 24. And so there's the fraction. I can reduce that to 1/2, or I can put as a decimal 0.5, or as a percentage, it's 50%. So any one of those three is a probability of landing on red. We do the same thing for probability of landing on yellow. Okay, so this time it's the number of times we land on yellow over the total number of trials. So we landed on yellow 4 times over 24. So that's equal to 1/6. Now, like I said, 1/6, we already saw this, 1/6. If I turn that into a decimal, I have to do some rounding. So I'm going to leave room for a little bit of more accuracy there. So 0.17, and that's equal to 17%. Okay, and then the last one, probability of landing on blue. That's equal to the number of times we landed on blue over the number of trials. So in that case, it was 8 times we landed on blue out of 24 times. So if I reduce that fraction, it's 1/3, which is equal to 0.33, repeating, which is 33%. Okay. Now, if you did everything right, if you add the percentages, 33, 17, 50, they should add up to 100%. Or if you add up the decimals, they should add up to 1. Or the fractions should also add up to 1, and they do in all these cases, even with our rounding. So that's a good sign. Now, determine the sum of the probabilities and what it means. So I'm basically going to add up all the, so I won't put the full landing on red, I'll just probability of red plus the probability of yellow plus the probability of landing on blue. If I add those up, now I'm going to use the fractions because the fractions are exact. So that's 1/2. Actually, I'm going to use the over 24. It's easier to add then. So 12 over 24 plus 4 over 24 plus 8 over 24. And I'm sure everybody saw this coming. This is equal to 24 over 24, which is equal to 1, which means 100%. Okay, so what does that mean, that sum of these probabilities? Well, it means because the sum is 100, or 1, depending on what units you're using, it means that there's no chance of landing on any other color. Okay, because it's 100%. So if I was putting that in words, it means the spinner can only land on red, yellow, or blue. Okay. Now the last part's it's kind of interesting because we, like I said, we never had a picture of the spinner, but what we're going to try to do is draw a picture of what the spinner might look like. So obviously we're going to start with a blank circle, okay, with the middle, and I'm going to look at each probability. So if I look at the red, okay, I landed on red half the time. So if I take 1/2 the time, that was my probability up here, and if I'm going to draw parts of a circle, I'm going to start with the degrees. So it's 360 degrees to go around. So how many degrees would the red be? Well, that's 1/2 of the total circle. So that's 180 degrees. So if I go to the circle, and usually what you do is before you even do this calculation, you draw a line from 12 o'clock to the middle of the circle and you start from there. And now we just determined that red is 180 degrees. So basically I start here and I'm going to go clockwise. So 180 degrees there means it's basically a straight line. So this section here would be red. It takes up half the circle, so that confirms our calculation here. Okay, so what about yellow? Well, we landed on yellow 1/6 of the time, so 1/6 of 360 degrees is 60 degrees. So if I keep going from where I left off here, if I measured 60 degrees with my protractor, this might be the only time you use a protractor in high school. So this would be 60 degrees roughly. So this would be yellow. And finally the blue. We landed on blue 1/3 of the time. So 1/3 times 360 is 120. And if we did everything right, this remaining section should be 120, and it is. So there's my blue section. And to confirm our calculations, if we add them all up, we get 360, which means we've covered the whole circle, so that confirms it. It also says, can you be certain this is what the spinner looks like? And the answer is you can't be. You can't be entirely certain. Of the shape, since it's only based on 24 trials. So just like the experiment we conducted with the, probability of rolling a 2, like I said, the more and more times you conduct that experiment, the more accurate your results will be. So if we spun this instead of 24 times, if we spun it 1,000 times, we'd be much more certain of what this looked like. There could be a chance that the really slim sliver on the spinner that's purple, and maybe that's only like 2 degrees. And when we spun the spinner 24 times, we never landed on the purple. But if we spun it 1,000 times, maybe we actually hit it. The amount of time that would give us that little sliver. So, and even with just these 3 colors, if we're certain it's just 3 colors, the shape, the allotment of space for these 3 colors would change the more and more you conducted experiments. Okay, so that's our first example. Okay, so this is another experimental probability. So we're looking at data and analyzing it. So this time We're at a pizza shop. He is the manager of a pizza shop. The table shows the number of pizza slices ordered during the lunch rush over several days. So we've got 3 types of pizza: pepperoni, Hawaiian mushrooms, and this is the number of slices that were ordered for each type of pizza. So the first question is determine the experimental probability that a customer will order each type of pizza slice. Okay, so again, we're going to actually count the number of trials. So in this experiment, you would say a trial is every time a customer ordered a pizza, we tracked what type they ordered. Okay, so the number of trials would be, the sum of those numbers there. So it's 98 plus 48 plus 51, and that is equal to 197. So the number of trials is the number of pizza slices is 197. So the probability of ordering a pepperoni, I'm going to shorten what I might normally say in here just for the sake of space. So the probability of ordering pepperoni is the number of pepperoni ordered over the number of trials. So the number of pepperoni was 98, and there's 197 slices ordered. That's equal to, now in this case, these aren't, exact, these are long decimals, so I'm actually going to put a couple more decimal places than I might usually, so 0.497. If we do the same thing with the Hawaiian, I guess I should capitalize Hawaiian. This time it's the number of Hawaiian slices over the total number of trials. That's 48 over 197, which is 0.243. And finally, the number of vegetarian is how many vegetarian slices were ordered over the total number, or the number of trials. So this time it's 51 over 197, which is equal to 0.258. You can see the importance of the extra decimal place because these two numbers are pretty close together. So in order to make sure that we're as exact as possible, we put in that third decimal place. Okay, so we could put this as a percent as well: 49.7, 24.3, 25.8. If we add these up, I don't think we're going to get exactly 1. I think it's going to be a little bit under just by looking at the last 3 numbers here. And that's to be expected because we rounded each of these decimals. You should be very, very close to 1, but you might be off by, a couple hundredths of a decimal place, which is what we're off by. Okay, based on this information, what advice should Tia offer her chef in order to be ready for the lunch rush? So based on this data, it basically is saying that about half the pieces ordered are pepperoni, and about 1/4, 25%, are the other 2 types. So the advice that she should give is they should make half the pizzas pepperoni, uh, 1/4 of them should be Hawaiian, and 1/4 vegetarian. And that's just so that, you don't run out of pizzas quickly and you're not left with too much extra pizzas. So you're basing future demand for the pizzas based on what has happened in the past. So, and that's fairly normal. Okay, so that was another experimental probability. The question here, example 3, is using dice or die. Many board games involve a roll of 2 6-sided dice, because it's 2, to see how far you may move your pieces or counters. What's the probability of rolling a total of 7? Well, this is something that's not instinctive as to, well, how many different ways can you roll a 7? So what we do for when we have two dice is, and this is really standard, is to draw a 6x6 table. Okay, and the top, I'm going to number 1, 2, 3, 4, 5, 6 possible outcomes of one of the die, and same thing on the side. So I could label this as die number 1, die number 2. It doesn't really matter which is which because they're the same in terms of outcomes. But what we're going to do is we're going to, each of these cells or entries, we're just going to add up the total. For example, we get a 1 and a 1, that's a total of 2, and 1 and a 2, that's a 3, and so on. You can just see we're adding 1 to the row, and we do the same thing here. 1 plus 2 is 3, 2 plus 2 is 4, and so on. It just keeps increasing by 1. 1 plus 3 is 4, 2 plus 3 is 5, 6, 7, 8, 9, and I'll just finish this off. Okay, so these are all the possible outcomes of rolling two dice if you add up the two dice together. So you can look at it and see, well, there's, you know, in terms of getting a 7, it's a pretty common thing. It can happen all these times. So, you know, how many possible rolls are there? Well, that would be 6 times 6, or the number of entries here. There's actually 36 possible rolls you could have, and out of those 36, there are 6 here that are 7s. Okay, so you could just count that up and say, you know, if we're doing it mathematically here, okay, the number of outcomes is 36. Notice I used the S this time instead of T, because S is the outcomes, theoretical outcomes, whereas T would be trials. Okay, if we were actually rolling two dice over and over, that would be trials. Okay, so the number of times we actually get a 7, so I'll say rolling a 7, that is equal to 6. 6 times. We already counted those up, so therefore the probability of rolling a 7 is equal to 6 over 36, which is 1/6, or 0.17, or 17%. Okay. Now, one thing you could also look at this. You notice there's no 1. You can't possibly roll a 1 with two dice, and the highest you can get is a 12. So if somebody asks you, well, what's the probability of rolling a 13? You could actually, well, you might know this intuitively that you can't, but you would see how many times 13 appears. It's 0. So it'd be 0 over 36, which is 0. Okay. You can also see here that 7 is the most popular roll. If you added up the other possible outcomes, you can see rolling an 8 and a 6, that's 5. Rolling a 2 or a 12, that's once. So those are pretty rare. So that's how you mathematically calculate the probability of rolling a total on two dice. Okay, example 4. We're going to look at the complement of an event. So complement, this is described in the key concepts, but this is a lot like the indirect excuse me, the indirect method. When we're looking at counting number of ways of counting something, sometimes it was easier to actually count how many things you don't want and subtract that from the total. So it's just kind of the same thing with probabilities. You might be asked to find the probability of something complicated happening, and it might actually be easier to find the probability of that thing not happening. Okay, so if we want the probability of a complementary event happening, it's just 1 minus the probability, or 100% minus the probability, depending on your units. Okay, so this is a good example of this. So what's the probability that a randomly drawn integer, and remember the word drawn just means selected or picked, randomly drawn integer between 1 and 40 is not a perfect square. Okay, so I'm going to actually use events this time. So I'm going to define for the first time an event. So I'm going to say the event A is when the number drawn is not a perfect square. That's what we want. Okay, now if I was doing this without the complement, I would actually have to count up how many numbers between 1 and 40 belong to this. Okay, how many numbers are not perfect squares? So it's easier to actually count up the ones that are. So what I'm going to do is I just define the event A. I'm going to define the complement, which is all the other numbers. So so the definition of A prime, which is another way of saying A complement, the number drawn is a perfect square. Okay, so that's a lot easier to work with. So I'm actually going to say that I know the numbers that are perfect squares between 1 and 40. Those numbers are 1, 4, 9, 16, 25, and 36. Okay, and I can actually add those up quite easily. So the number in event A is 6, if we count them all up. So I can do this one of two ways at this point. I could actually, if I know there's a total of 40 numbers, I know if the number in A prime is 6, I know the number in A is 40 minus 6, which is 34. Okay. So I'll show you the two ways of doing this now. I could stick with A. Probability of A happening is the number of times A does happen over the total number, which is 40 numbers picked, or numbers chosen from. So the number in A, we just calculated, that's 34 over 40, and that works out to 85%. Okay, so that is the answer to the question. I also could have done it a slightly different way. I could have said, well, probability of A is equal to 1 minus the probability of A prime. Okay, this is the formula I was telling you about. It's in your key concepts. So if you knew the probability of drawing a perfect square, the probability of not drawing a perfect square is 1 minus the probability of drawing a perfect square. So in this case, this would be 1 minus 6 over 40, because there's 6. Probability of drawing a perfect square is 6 times out of 40. So that's also equal to 34 out of 40, which is 85%. So you can see we got the same answer, two different ways, but we didn't actually count up how many numbers were not perfect squares. We kind of started with the complement event, counted those numbers, and used that to help us. Okay, so that's the complement. It's very similar to the indirect method that we use for counting. Okay, subjective probability. This is the third type of probability I mentioned. This is the gut feeling about the probability of something. Probably not so much based on mathematics and experiment, just on what you think. So probability, and these numbers will be different for most people, but they should be in the same ballpark, hopefully. Now the next pair of shoes you buy will be the same as the last pair you bought. So I would say for myself, I'll put a range here. I'll say 60 to 90%. Okay, just because different brands and different models have different sizes. You're not going to have the same size every time. But if you're a person who buys the same shoe every time and you just wear them out and keep buying new ones, well, your probability, or that person's probability, will probably be close to 100%. The second one, an expansion baseball team will win the World Series in their first season. Just so you know, expansion baseball team means it's their first year playing. So usually expansion teams don't have the best players on them, and they don't have a high chance of winning the championship. So personally, I would say 1 to 2%. The probability that the next person to enter a certain coffee shop will be male. Well, not knowing the coffee shop or, much about the neighborhood, I'm going to randomly, well, not so randomly, but 45 to 55% is a pretty safe bet. Okay, but I mean, it could be a coffee shop that's right next to a yoga studio, and maybe their clientele is 80% female. So it depends on the situation. So it's very subjective, and that's why it's called subjective probability. Okay, last example. So this actually is in the textbook. So now they put this as their first example. I found it kind of intimidating to students to see this as the first question. So basically, you've got two players, A and B, player A and player B. You give each of the players a randomly picked number that's on a slip of paper. So the slips have 1, 2, and 3. So player A could get a 1, a 2, or a 3. Player B could get a 1 or 2 or 3. So what we do is we do a bit of math here. So we actually add the numbers that they get and also multiply them. And if player A gets a point if the product, when you multiply the two numbers, if that's bigger than the sum, player A gets a point, and if the addition of the two numbers is greater than the sum, that player gets a pick. Now, if both of the numbers, the product and the sum, are equal, nobody gets a point. So it says, let event A be a point awarded to player A, and list all the outcomes that make up event A, and what's the probability that player A gets the point? What's the probability that player B gets a point? What's the probability that nobody gets a point? So this is pretty confusing. So the best way to do it is, well, start off with all the possible outcomes. So we're not really doing trials. We're just doing what could happen in this situation. Okay, so this is going to be theoretical probability. So I'm going to put all the possible outcomes here along all the different types, and then I'm going to put which number did player A get, which number did player B get, and then we're going to calculate the product and the sum of those two numbers, and who is the winner of this outcome. So these are going to be rows. Okay, now how many outcomes could there be? Well, each player can get 3 possible numbers. So if there's 3 choices for A's number and 3 choices for B number, that's 3 times 3 outcomes. So I'm going to have 9 possible outcomes. So I'm going to put them here in the columns. Okay, so we're going to define each outcome as, well, what number did player A get? What number did player B get? So I can go through all the different outcomes. So the first one might be they both get number 1. Next one could be player A gets 1, player B gets 2, 1, 3. So these are the 3 outcomes. If player A gets a 1, then we can do the same thing for 2 and 3 for player A, and player B could get 1, 2, or 3 for each of those. So those are all those are defining each of the 9 outcomes. Okay, so what happens when we do the product and sum? Well, it's just multiplying and adding. So I'll do all the products and all the sums. So 1 times 1, 1 times 2, 1 times 3, 2 times 1, 2 times 2, 2 times 3, 3, 6, and 9. Okay, now we go back and now we add them. We get the sum. So 1 plus 1, 1 plus 2, 1 plus 3, 2 plus 1, 2 plus 2, 2 plus 3, 3 plus 1, 3 plus 2, 3 plus 3. Okay, so now we compare. So kind of have to go back and remind ourselves what happens here. So player A gets a point if the product is less than the sum. Player B gets a point if the product is greater than the sum. Okay, so in this case the sum was bigger, so A is the winner. So maybe I'll just scan through here. So see where the sum is bigger, that means A wins. So sum is bigger there, there, there. Nope, nope. Oh, it is here. And not there. Okay. So it looks like A's got a pretty good chance of winning here. And now we'll go back. Okay, when is the product bigger? Well, here it's the same. So actually nobody wins there. And this means that B would win, and also B wins here because the product is bigger. So if we define the events, so player A gets a point. Event B, player B gets a point. And event C, I don't think they ask us for this, but I'll just define that as nobody gets the point. Because I spelled this wrong. Okay, so we define the events. Now we do the probabilities. So the probability that A happens, player A gets the point. So we count up how many times A won. So that was 5 times out of a total of 9. So 5 nines. And that's equal to 0.56 or 56%. Player B wins 3 times out of 9. So that's 1/3. Works out to 1/3, so 33%. And then nobody winning, that happened once out of 9 times. So that's 0.11 or 11%. Okay, I could put words around this, but the way I've defined the events and then the probability of those events happening, that's a pretty solid answer. But if you wanted to, you could put the probability of player A winning is 56. In this case, I think this is fine. And one other thing you can do is you can add up the probabilities, and if we do, we get 100%. So that's a kind of a little safety check that we did the math correctly. Okay, so that's it for today. I know we covered a lot. Thank you for your patience. A lot of new terminology. The important things is some of the 3 ways of calculating probability: theoretical, experimental, and subjective, and some of the terms we used when we do those calculations. Okay, so have yourselves a great day, and we'll see you on the next lesson.